Recording is on.
Okay, so I hear the message. All right, yeah. So thanks everyone for coming to this talk. It's about a problem in convex geometry called the Buseman-Petty problem. And so essentially this talk is very simple in its outline. There is a problem, a very classical and a very interesting problem, and we are going to look at a solution to it. And this is the outline of the talk. Initially, we'll give some motivation and some background and so on. And then we go on to the statement of the Buseman-Petty problem. And then we move around in terms of the background needed for its solution. And then we give the solution. And the reason I have stated it this way is because like if at some point in this talk you get a bit disoriented and so on, then you can always reorient yourself knowing that this talk is as simple as a problem and its solution. And I must tell you that this is not really a research talk. It's more like an expository talk. And this problem was actually solved in 1999. So yeah, so it's mostly me talking about a solution which was done by Koldovsky. Okay, and on the way, so I found it very fascinating because like a bonus gift on the way, as you see, is like we'll actually see a very concrete formula for the volume of affine hyperplane sections of the standard cube center of the origin. And in fact, it will actually be a corollary of a more general result about volume of central hyperplane sections of any origin symmetric convex body. Okay, and I hope my sneezings and like this very unfortunate cold will not affect this talk too much. So I apologize from the beginning for that. Okay, so yeah, before we dive into that problem, let's talk about some basics, like some basic definitions. So first of all, the basic framework is convexity. So a set K in Rn is the Euclidean n-dimensional space, and is said to be convex if you have like 2 points in that set K, then the line segment joining the points X and Y is completely contained in K. Then you say that this set K is convex. And you say that a convex subset of Rn is a convex body if it is compact and also has non-empty interior. So some parts of the literature do not really demand this non-empty interior part, but in our case we will want that, and I'll explain it just for simpler notation. That's all. And we have examples. If you imagine like convex bodies, cubes, polytopes, very simple examples like polyhedron and so on. And unit ball of any norm on Rn is in fact a convex body. And you may recall that all norms on Rn are in fact equivalent, topologically they're equivalent, but the unit balls could look quite different. And but all of them have to be convex simply because of the triangle inequality. And the boundary of a convex body is denoted by partial K. Okay, so there is actually a correspondence between norms and origin symmetric convex bodies. So that's what we're going to discuss a bit now. Like convex bodies is what we just talked about. It's a kind of a generic notion. Yeah, so what are norms on Rn? They're effectively ways of like taking a vector and assigning a number to it, like a non-negative real number, which is supposed to represent its length in some sense. So one of the first things you want of it is that it should obey the triangle inequality. Norm of x plus y should be less than or equal to norm of x plus norm of y. And if you scale, the norm is actually scaled by the modulus of whatever scaling factor you're using. Like in the case of like real scaling, absolute value lambda just is a matter of sign changes. Like if you're scaling by -2, then the norm is scaled by +2 and so on. So you have this scaling, or you could say it's a homogeneity of the norm of degree 1. It's a homogeneous function of degree 1. And then you have this positive definiteness, kind of, that norm of x is always bigger than or equal to 0, but it's equal to 0 if and only if your vector is already the 0 vector. So the only thing with like 0 length is the 0 vector. And very familiar examples are like, for example, L infinity norm, where you have all these coordinates x1 through xn, and you just take the supremum of that, and it satisfies all these properties. And also the Euclidean L2 norm, or what we also call as L2 norm, where you sum the squares of the coordinates and take a square root. And then LP norm for p from 1 to infinity. Then you sum the pth power. I should actually write absolute value there. Yeah, it's absolute value of xi to the p. and then you take the P through. This also turns out to be a norm from Minkowski's inequality. So, sorry. Yes, I got a phone call. Yeah, so sorry about that. Yeah, so anytime you have a norm and you take its unit ball, meaning all those vectors whose norm is less than or equal to 1, then it is an origin symmetric convex body simply because of the thing we saw here, this vector. It's the scaling of this vector, the norm of that is given by like modulus of the scaling factor times the norm of the vector. So that means that minus x has the same norm as x. So for p equals 1 to infinity, these are this is what like the unit balls look like. And p equals infinity effectively gives you like a hypercube, like in dimension n, and p equals 2 gives you like the familiar sphere. And this is actually not a convex body. And of course, p is half, which is less than 1. But this is, in fact, all the results we're going to talk about also hold for things known as star-shaped bodies, not just for convex bodies. But just for the sake of simplicity, we'll focus on convex bodies. But it's good to keep in mind that these results are actually general enough. And star-shaped bodies just means that instead of saying that for any x and y, the line segment joining x, y lies in that body. That's what we say when we want a body to be convex. But star-shaped means that you pick x to be a distinguished point, which is the origin. So any point and the origin, if you join, then the line kind of lies within that body. So that's what it means to be star-shaped. Okay, so for any p bigger than 0, you actually get if you want to call it a unit ball, that will actually be star-shaped bodies. But yeah, but we'll be focusing on only the convex part. All right, so here we said that like from a norm, you get an origin symmetric convex body, but the converse also holds. Like given any origin symmetric convex body, you actually get a norm. And here, actually, the fact that in the very beginning I mentioned that I'll be demanding a non-empty interior of the convex body, that's because if you didn't demand that, you just said, okay, it's just a compact convex subset, then what you would get is semi-norms. Like if there is no interior point, you might not have that positive definiteness kind of thing. So it's just a matter of like convenience. Yeah, so how do you get a norm from origin symmetric convex body? So effectively what you do is you have this body, and let's say this is the origin, and any point here. So essentially you demand that this boundary of this convex body actually be the unit ball. So what you want is if x is in the boundary of k, then you effectively just say that norm of x is equal to 1. And then the rest you just assign by scaling. So norm of x and norm xk sub k is also known as the Minkowski functional. So this is just demanded to be 1 when it's on the boundary, and rest you can clearly guess that if I'm like halfway from the boundary, like from the origin, then I just assign the number half. And if I'm like 2 times from the distance from the boundary, then I assign the number 2 to this k norm, so to say. And this is also a homogeneous function of degree 1. And it's kind of just to see why this is a norm. So this was the intuitive way of seeing what the norm is. But if you define it as it's the smallest lambda, such that when you scale k by lambda, x is still in there. And if you go any lower, then x will be outside of lambda k. So if you demand that, then what you have is x is in times k. Yeah, I don't have my tablet with me, but so this, and then similarly for y, you have that. Then when you add x plus y, it must belong to norm xk plus norm yk k. But by definition, norm of x plus y is the minimum such lambda. So yk. So it's a kind of straightforward. If you define it this way, then you define it this way, like the way it's written here. Then it's very easy to see that this is actually a norm. So there's a one-to-one correspondence between norms and origin symmetric convex bodies. So that's why we do care about this extra adjective, which is origin symmetric. Okay, so So again, like I want to remind you what the talk is about. It's about a problem called the Buseman-Petty problem and its solution, right? So far we're just building up definitions and the players in this act, you could say. Okay, so before we turn to the Buseman-Petty problem, there is a corresponding thing which we'll talk about known as the Cavalieri's principle, which effectively says, let's say we have all these solid bodies, and let's say all of them have the same height. So height h, and at any height, let's say if we take a horizontal cross section, let's say the area is the same for all of them, then Cavalieri's principle says that the volume of all these objects must be the same. And this is pre-integral calculus or something like that. Now we clearly know that, okay, each of these cross sections is defines a function from 0 to h, and this volume is like integral of that function. So if two functions are the same, the integrals have to be the same. That's effectively what Cavalieri's principle is telling you. So if area of cross sections are the same, then the volume is the same, the way you build it up. But it also says a bit more if you think about it. It's like if I have f bigger than or equal to g, then again, it's a very simple consequence of the theory of integration, that integral of f is going to be bigger than or equal to integral of g. And effectively, if you interpret in this Cavalieri principle thing, that if I have horizontal cross sections of two bodies of the same height, and one of the cross-sectional areas actually dominates the other one, like at each and every point, then the total volume must dominate the total volume of the other. So if f is bigger than or equal to g at each point, then integral of f is bigger than or equal to integral of g. And this kind of way of looking at an object by looking at cross-sections is actually, it's not just, first of all, it's a very nice way of like building things from lower dimensions, and we see it, these kind of ideas all the way in mathematics, like in topology and whatnot. Like you first try to understand low dimensional things, you put them together, then build more complex objects and so on. So this kind of, at least philosophically, these kind of ideas do make a lot of sense. But even if you want to go a bit more practically, then if you think of CT scans or CAT scans, like computer axial tomography scans, there the idea is also to rebuild a body. It's actually more a more strict recipe than just talking about volumes. It's also talking about the exact shape of the body by looking at cross sections. What does a CT scan do? Let's say you have this object with some absorption coefficients. Like denser parts assume that like they absorb X-rays more, so absorption of X-rays, I should say. And typically this will be like a human body or human body part. And then essentially you pick a direction and send an X-ray. And of course, it's a very simplistic model, but let's say this is the thing that exits. You have the entry, and then you have the exit. And what we know is what intensity we sent in, what intensity we got out, right? So effectively, we know the integral of this absorption coefficient along this line. So from that, we actually want to reconstruct this body. So effectively, what we have information is we want to reconstruct f, which is actually a function compactly supported, if you will, on Rn. So this is the function we want to figure out. And what we know is actually integral of f along various directions. You could say and these lines you could if you will, these are like elements of the affine Grassmannian, one-dimensional, like the set of all lines in Rn, something like that. And for each line is associated a number, which is the integral along that line. So effectively, that this transform will take let's say f1n to real numbers. And from this function, you can actually, and this is something which will come up in the next few slides, something called the Radon transform, and you can actually invert the Radon transform under certain assumptions, and that's what essentially like CAT scans are all about. Of course, so again, this is just to motivate the fact that building up a body from cross sections can actually have very like concrete real world implications. And of course, this is how we do math and like science and all. We have different probes, we probe at a thing, look at it from different points of view, then we integrate it together to have a full picture. Okay, so here we were looking at horizontal cross sections, and now another way to look at it would be to actually look at, let's say, central hyperplanes sections of origin-symmetric convex bodies. We're trying to draw some analogy with Cavalieri's principle. You have K and L, and what you know is, let's say I pick a direction xi, and we can always assume xi to be a unit vector, and then I take essentially the orthogonal part, or the orthogonal hyperspace or hyperplane, the n-1 dimensional thing, and it has some intersection with this convex body, and we compute this area. So essentially the broader question will be, how much can we know about the actual object if we actually know these areas? So Minkowski's uniqueness theorem kind of tells you that if these n-1 dimensional cross sections for two origin symmetric convex bodies K and L, they're equal, then it is actually true that the total volume is also equal. Volume of K, the n-dimensional volume of K, is actually equal to volume of L. In fact, we'll see that K will actually be equal to L, unlike in the Cavalieri's principle case, where we were just stacking things together, so we didn't have control over the actual shape. We just knew what the volume is going to be. It's going to be equal. But here we can actually say more. We can say actually K equals L. And again, if we go back here, we had this inequality thing. So can we make a remark of a similar nature in this case? So that's the Buseman-Petty problem. So we have come to our problem finally, which is let K and L be origin symmetric convex bodies in Rn, such that the n-1 dimensional volume of these hyperplane cross sections, the corresponding ones, are dominated, like L dominates K in that sense. Then the question is, does it follow that the total volume is dominated of K is dominated by the total volume of L? And this is actually like from the 50s, and the problem has of course, like many such problems which are simple to state, it has a checkered history. In fact, initially there was a probabilistic proof that I'm kind of giving away the answer right now, roughly, that beyond dimension 10 the answer is actually false, like in the sense you can find counterexamples to this claim. And slowly, eventually, it was figured out exactly where that transition happens and so on. And even, in fact, in '94, I believe, there was a paper in the Annals which said that, like in R4, they found a counterexample, but it was in fact incorrect. In fact, in R4, this assertion is in fact true. And it was, again, corrected in '98, and final solution was given in 1999. And the great thing about the solution is it's actually not a case-by-case kind of, it's not treating different dimensions differently. It actually gives you a kind of like a method which treats all dimensions equally. Eventually, it just becomes a matter of reading of certain conditions, like depending on this value of n. So the answer is actually, it depends on n. So answer. But exactly what we'll like talk about at the end. Okay, so what's the time now? All right. Okay, so now again, so now that we have stated this problem, so we'll do a brief review of the techniques that will be needed. I'm guessing some of you may be rusty on these things, so I'll just try to be, I'll try not to be overtly technical in these aspects, but I'll say the main ideas that are involved. Okay, so first of all, like what's a Fourier transform? So Fourier transform, effectively you have a function and you effectively do a change of basis in some sense. Like you can think one basis is like Dirac delta functions, like point, or you could say position basis, then you transform into some sort of frequency basis. But if you want to be very like strict of like what functions does it act on, where does it end up, like usually when you start with the theory of Fourier transforms, you start with, okay, let phi be an integrable function, and then this is the way you define the Fourier transform. And then you have the Riemann-Lebesgue lemma, which will tell you that, okay, this is actually a continuous function vanishing at infinity. But yeah, it's just one remark I want to make here is, so this is, there are like a few definitions of Fourier transform one might encounter in the literature. Of course, all of them are the same modulo certain constants. Like for example, some people might put a 2 pi around here, like instead of minus I, you have a minus 2 pi I. So it typically is a matter of taste. Like for example, if I put a 2 pi here, this result I have written here will actually be much more beautiful. So this is Plancherel's theorem, which essentially tells that the inner product, like in quotes, of f and phi is actually same as the inner product of f hat and phi hat, where f hat means the Fourier transform of f and Fourier transform of phi respectively. So essentially it's telling you that Fourier transform is like a unitary operator. And on Watt space, in fact, this this definition we have here is actually bounded in L2, like on functions on L1 intersection L2. So you can extend it to L2 spaces and so on. And Plancherel's theorem essentially is talking about L2 functions. Yeah, but the thing is, once you go to the level of distributions, you can be quite a bit more sloppy. So here we have to keep track of where we're starting, where we're ending, and so on. But in maths, we don't like that, right? Like we don't want things to be that specific. We essentially earn for the right to be sloppy, kind of. Like for example, one example I like to give is like you start with real numbers and you want to solve polynomial equations in that. So instead of trying to say that, okay, the maximum number of roots you can have is less, the number of roots you have is less than or equal to n, you kind of prefer to go to complex numbers and always say, okay, there are exactly n roots. I do my math, do my whatever calculus I have. At the end, maybe I'll ask myself, okay, which of these roots are real or not? So I have some sort of completeness, algebraic completeness in that case. Here, some sort of like, you kind of get the right to differentiate willy-nilly and like take Fourier transforms willy-nilly and so on. So I'll talk about distributions a little bit. But the whole point is essentially you want to use this calculus, like the way of calculating to, and not have to care about too much about like what my function is and what not. Okay. Yeah, before we talk about distributions, just a brief statement about Radon transform, which we already saw in the context of CAT scan, CT scan, and so on. So here, essentially, phi is an integrable function on Rn, which is also integrable on every hyperplane. So here there is a catch. Like for example, when you talk about Fourier transforms, you are talking about L1, like you have some measure and so on. But here, when every hyperplane has measure 0, right? So what does it even mean to integrate something like that? So here you actually need a bit more nicer functions. Like typically, if you have continuous functions and so on, you know exactly what you mean by these statements, like integrating on hyperplanes, like lower dimensional subspaces and so on. So this is actually a lot more like finer theory than Fourier transforms. In fact, there is no unique distributional equivalent of Radon transforms. So yeah, that's just one like technical point to keep in mind, but that wouldn't affect anything in our discussion. Okay, so the Radon transform is effectively defined as, so what is this? X dot xi, this is actually a affine hyperplane, right? If t were 0, that would be a central hyperplane. So effectively you have this unit vector xi. And if this were the origin, then you would have some sort of hyperplane like this. Or if you want to shift it by t, like something like this, then you get x dot xi equals t. So essentially integrating this function phi on that, and you are assigning to this coordinate xi comma t. So effectively, like roughly, you can think of it as somewhat people are tempted to say polar coordinates, but it's not quite that. And I like to remind that it's like more like this. If in high school we learn different ways of writing a line, one of the ways we learn is every line you can represent using, except the one passing through origin, that it has a distance from the origin, that's h, and there is an angle associated with that, alpha, right here. So these xi and t's are exactly that. So it's not exactly like polar description of that, because the space, as I said, is the affine Grassmannian. So this is the parameterization of the affine Grassmannian. Here in this case, it's n-1, comma n. So this is the Radon transform. And there is, of course, like also a very straightforward connection between Radon transform and Fourier transform. In fact, this is the connection that is used in doing the inverse Radon transform, because we have a very nice inverse Fourier transform. So yeah, this is just a technical result to say that Radon transforms and Fourier transforms are quite related. So let's just assume that this connection exists. And you can also talk more specifically, instead of on Rn, you can talk about Radon transforms on the sphere. And effectively, all you have to do is you have this uniform measure on the sphere, and when you take these hyperplane sections, then what you end up is with all these lower dimensional spheres. And then you integrate things on there. So effectively, earlier we just had xi perp, like this x dot xi equals t is actually like translated version of xi perp. But here actually we care about the central hyperplanes which intersect the sphere. So this is what is called the spherical Radon transform. And it has a nice property that if you have two continuous functions f and g, then essentially it's like some sort of self-duality, like R, F, and I'm going to use this notation quite often, this like inner product kind of notation, so sometimes even when we don't have a Hilbert space, and which is actually pretty standard if you want to think in terms of like this functional acting on this element of your vector space and so on. But the idea is this expression will typically mean this integral. There is an integral of product of these two on the appropriate space. Yeah, so this is true. And this is also something we'll be using, the self-duality of this of the Radon transform. And another thing to keep in mind is a lot of the things we'll be dealing with are homogeneous functions, and they're completely determined by their values on the sphere. That's why the sphere is important, because even if you want to work on Rn and you have a homogeneous function, like we are happy to know what it is actually on the sphere. Okay. So yeah, so before we move on, this is the last bit of like background I will be giving of being sloppy, like in the sense, or in another way you could say that it's a way of making your sloppy arguments rigorous. So in a sense, you could have said like, okay, Dirac was talking about Dirac delta functions in late 1920s or early 1930s and so on. And then there was a body of literature talking about these kind of generalized functions. And then Laurent Schwarz, he eventually put them together in a like a logically like meaningful manner, like in his distribution theory. And the way it works is you effectively, instead of thinking of functions as just functions on a space, you think of as functionals on an algebra of functions. And typically here you have this space of test functions or Schwarz functions, which are infinitely smooth functions. And not only that, they decay rapidly. In the sense, not only do they vanish at infinity, also their derivatives and all derivatives vanish at infinity. And in fact, they vanish more rapidly than 1 over any polynomial. So that's what these are, your test functions. And in fact, you can just imagine like functions with compact support, which are infinitely smooth, will naturally become Schwarz functions, because after a certain point, they're just zero. So they're like going to infinity faster than any like 1 over absolute value k. Anyway, so these are the test functions. And tempered distributions. So distributions are effectively functionals, like in the sense, the way I would write it is distribution U acts on a Schwarz function phi. So essentially, use a continuous function on something called the Schwarz topology. Effectively, it's a topology which is taking into account this decay and the derivatives and so on. So all of these decay of the derivatives, and so it's a topology which is keeping track of like convergence in this rapidly decreasing functions. And the great thing is that the Fourier transform is a bijective map on the Schwarz space of functions. And the way you define Fourier transform of distributions is using the Plancherel kind of thing. You effectively say that you had phi hat. Again, like depending on notation, you will probably have to put in the 2 pi to the n, but let me be a bit sloppy and put a c here. And depending on your definition of the Fourier transform. And yeah, so this is the way you define it. In the sense, first of all, note that as phi varies over all the Schwarz functions, phi hat also varies over all the Schwarz functions. So in fact, if I define it this way, U hat is acting effectively on all Schwarz functions. The only thing you have to worry is about continuity in the Schwarz topology. And that turns out to be true. And
Soumyashant, can you say a few things about Schwarz topology? I mean, is it like what kind of sequences of functions will converge?
Right. So you have a bunch of semi-norms. Okay, so I'll just say the word semi-norm. Will just okay. So you want something like the norm of a function one of the semi-norms could be like x to the, let me stick to one dimension. In more dimensions, you will just put in all the partial, like x1, x2, xn, and all those polynomials. So x to the n times partial to the k of phi of partial x to the k. So you have all these pairs, right? N comma k. So these will define some semi-norms. And you essentially want, so you will say something like phi goes to 0 if in fact, like it's in the weaker sense, like in the sense in each of the semi-norms, phi has to go to 0. Does that make sense?
Yeah,
like,
sure.
Yeah, by the way, infinity. When I write this norm, I mean infinity norm of this, and that will make sense because these are all rapidly decreasing. So in fact, x to the n and kth derivative of phi will actually have an infinity norm. So if you index this by saying something like p n comma k of phi, so this is the norm, the nk semi-norm of phi, then you'll define the Schwarz topology as that, yeah, if phi n goes to 0, if it goes to 0 in each of these semi-norms. And in fact, that will define, it will not define a norm, but it will actually be, what's the term for that? It will be faithful, or like in the sense, you cannot have like phi n going to phi and phi n going to psi for two different things. Like something like that. It will, the topology will be Hausdorff or something like that. Yeah, so does that answer your question?
Yeah, thanks.
Okay, yeah. So yeah, effectively, essentially you're demanding that by doing this infinity kind of norm, that the rapid decay holds even in the convergence kind of thing. Okay. And once you do this, so Fourier transform has a very natural way of going to the theory of distributions, and distributions are actually, in a very loose sense again, they're not that exotic. I mean, at first glance, they look exotic. Okay, we have these functionals. Of course, functions themselves are distributions. Like, let's say, like locally integrable functions are themselves distributions because you just integrate f times this phi, you will get some number that will give a functional. But there is a result which talks at least locally that any distribution is effectively finitely many derivatives of a function. That function does not have to be differentiable in the typical sense, in the standard sense. Like, for example, if you have the Heaviside step function, it's a nice like locally integrable function and so on. If you differentiate this in the distributional sense, you get the delta function, the Dirac delta function, so to say. And you can differentiate this further and further. And all distributions kind of arise in this type of manner from some functions. So yeah, if you're trying to solve differential equations and so on, like instead of worrying, okay, how many times can I differentiate, how many times can I not, you just first try to do it in this type of framework and see like what you can get. Then you try to see, okay, is this a real function? Like a like honest to goodness kind of function. So that's the way you proceed. Yeah. Okay. So okay, I have like 20 minutes, right? 25 minutes, right? Hello.
You can go till 4:10.
Okay, yeah, so I have like 25 minutes. All right. Yeah, so another final thing, so notion we'll need is the notion of positive definiteness of a distribution. And a distribution will be said to be positive definite if its Fourier transform is actually positive distribution. And again, positive distribution is a natural thing. It just says that U is said to be positive if U phi is bigger than equal to 0 for positive phi. Like when phi is a Schwarz function which is positive. And this is the point where like inequalities start entering. Like if you remember Buseman-Petty, we have this volume less than this, and we want to conclude something. So positive distributions play actually a very important role there, as we will see. And there is this theorem which says that distribution is positive definite if and only if it is the Fourier transform of a tempered measure. Or you can think measure with the right decay properties. So tempered measure would mean that. Yeah. So this is the theorem that will also be useful, and you can see this is what I meant. Like initially you can say distribution is this and that, but typically your final goal is to try to prove that okay, my distribution actually eventually turns out to be a real analytic function, or maybe it turns out to be a measure, or something like that. So typically that's the way you try to proceed. And in our case, we will get a very nice measure out of all these distributions. Okay, coming back to the problem. So we have this origin symmetric convex body K, and let's take a direction xi. Xi is a unit vector in Sn minus 1, and this thing is the central hyperplane. But we take the affine things, like one by one you take cross sections. Then this will become a function of t, right? At 0 you have this area. Then a chi xi 0 is the central hyperplane section, the n minus 1 dimensional volume of that. Then you shift it by a distance of t in this direction of xi, and then you get ak xi of t. Okay, and it's a function on R. It's just like minus infinity to infinity, and since it's a compact body, what you have is that eventually it has to vanish. Like beyond these like edge points, you'll just be 0. So this function actually kind of retains a lot of information about the convex body, as it's not hard to imagine that is the case. And it's a very simple computation. If you look at this a k xi t, which is again, you translate this central hyperplane by t, and then you compute the volume of the cross section. You can just say that, okay, this is the affine hyperplane here. So we are integrating this indicator thing. This chi, by the way, is indicator function of 0, 1. So if my norm xk is less than equal to 1, which essentially exactly, so this statement, norm xk is less than equal to 1, exactly means that x is in the convex body. So it's if and only if. Norm xk is less than equal to 1, if and only if x is in k. Right. So effectively, it's just saying that I will put 1 if x is in the convex body and 0 outside. And that's what will be the area, right? We are integrating the function 1 on that. So now let's look at t equals 0. So that is the central hyperplane. And again, I will just do a change to polar coordinates. Then you have r to the n minus 2 chi. Essentially, norm xk has been just written as r times theta xk. And then we know that r can only go from 0 to 1 over norm theta k. Otherwise, beyond that, chi will give you a value of 0. So this is why you have this 1 over norm theta k. Because r times this, so r times this will give you 1, and beyond that, chi is 0. And then a simple computation just tells you that, okay, I mean, this is r to the n minus 2, so you get r to the n minus 1 over n minus 1. That's just simple integrals. And since this is a 1 over norm theta k, that's why you have this minus sign here. And if you recall, the Radon transform was exactly this kind of, spherical Radon transform was exactly this kind of description. So in fact, this is 1 over n minus 1 times the spherical Radon transform, which we denoted by r, of this function, norm theta of k to the minus n plus 1. So here we can already see that even talking about all these cross sections, very naturally, like this Radon transform has entered into the picture. Not only that, this function itself seems to be important. This norm theta k to the minus n plus 1. And a lot of this will be, so this is kind of the way Fourier transforms are coming into play here. So now we can give of course, like modulo details, we can give a quick proof of Fourier-analytic proof of Minkowski uniqueness. Remember, what was Minkowski uniqueness? It said that if the cross sections in any given directions, the hyperplane cross sections are equal for k and l, then the objects themselves are actually the same object. So for that, this is a lemma which we'll use, that if f is an even homogeneous function of degree minus n plus 1, and if you look back, this is exactly that, right? This is an even homogeneous function of degree minus n plus 1. So again, this theorem lemma will be applicable to this function. So if we have an even homogeneous function of degree minus n plus 1 on Rn, which is continuous on the sphere, again, like that is continuous on the sphere, the only issue is if you try to extend it, there will be singularity at the origin, because you have this 1 over thing. But so that's why the distribution theory is coming into play. You don't have to worry, you don't want to worry about these singularities, and you still want to be doing Fourier transforms. So here it's saying that the Fourier transform, of course, in the distributional sense, you will get some distribution. But here it's saying it's actually more than just a general distribution. It's actually an even homogeneous function of degree minus 1, which is again continuous on Rn minus 0, such that if you restrict to the sphere, the Radon transform of f is 1 over pi Fourier transform of f evaluated on the sphere. So essentially, if you look at the formula we have here, we have R of something, right? We can replace it with actually the Fourier transform. So then the previous page result can just be summarized as the following. If K is an origin-symmetric convex body in Rn, then AK is I0. Remember, this is the central hyperplane section in orthogonal to this vector xi. And so this is just a tautology, this first equality, just the definition. And then this is the 1 over pi kind of comes from here. 1 over n minus 1, we had that in the integral. And then essentially we have to take the Fourier transform of this even homogeneous function of degree minus n plus 1. And now how do we prove Minkowski uniqueness? So effectively, if we are told that AK xi is actually 0 is equal to AL xi 0, what does that mean? That Fourier transforms of this function, so if AK xi 0 is equal to AL xi 0, so effectively that means the same for the right hand side, right? So essentially it's telling me that Fourier transform of this Minkowski functional K is same, and then I'll take the inverse Fourier transform. And remember, in the sense of distribution, I don't have to worry about anything. So in the distributional sense, these functions are actually the same. And two convex origin symmetric convex bodies will have the same Minkowski functional if and only if they're actually exactly the same convex body. So this is effectively proving that the Minkowski uniqueness theorem, that K equals L, which implies K equals L. Okay, so at least the equality case we have some handle. Like now we are going to, and inequality typically like Fourier transform behaves well, right? It's just it's a formula, like it's a change of basis, that kind of thing. But once we come to inequalities, these kind of results become a lot more nuanced, right? Because I cannot say that if f less than or equal to g, that means that Fourier transform of f is less than or equal to Fourier transform of g, and those kind of things. So one has to be, one has to make a bit more nuanced argument. And so here, this is something I promised in the first slide. And I'm going to, like this theorem 9, I'm just going to replace K by, let's say, the hypercube, like for the L infinity ball. Then this is the formula you get. That if you have a hypercube and you take the cross section, and remember that for the, if you have this indicator function, like from -1 to 1, let's say, the Fourier transform is effectively the sinc function. This function is called the sinc function, sin x over x and 1 at 0, sinc of x. So this is why this formula is coming in. And so you can actually explicitly compute, you take any hyperplane section and then you can compute the volume, the cross-sectional area of that. And in fact, for some time it was thought that, like if someone asked you this question, like if you have like a hypercube, so what is this, the central hyperplane, which kind of gives you the maximum cross-sectional area? So for some time it was thought that it is the one which maybe a lot of us will think at first glance is the one which is orthogonal to 1 over square root n, 1 over square root n, which is like the main principal diagonal vector and the one orthogonal to it. But it turns out that it is actually false. That is not true. In fact, if you just take 1 over square root 2, 1 over square root 2, 0, 0, 0, you can immediately check from this formula that it will give you a bigger cross-sectional area. Again, I didn't give you a chance to think, so maybe some of you would have guessed the right. Actually, I'm not sure if this is actually the maximum, but this definitely dominates the 1 over square root n thing. Okay, you get the picture. And again, you can you have a similar formula for like any p bigger than 0, and all these discussion, again, I remind you that this is about convex bodies, but the formula is in fact true for star-shaped bodies, like the Fourier transform formula. So for p bigger than 0, not just p bigger than or equal to 1, you have this formula for the hyperplane cross sections. And here gamma p is the Fourier transform. I guess I probably want this to be less than or equal to 2 p. Yeah, I probably want p to be less than or equal to 2. So where gamma p is the Fourier transform of the function f to the minus norm x to the p. And of course, I don't know much, but it was very curious to me because I don't know if Parthanil is in this talk, but at some point he had mentioned to me about, okay, stable random fields and like talking about characteristic functions, like random variables whose characteristic function looks like this. So somehow this kind of appears here, like in this formula of cross sections of LP balls, like Fourier transform of the function. And if you think of characteristic functions as Fourier transforms, then this is what you get. And beyond p equals 2, I guess you don't get positive definite functions. Okay. Yeah. So this was one of the main points I wanted to impress upon because I thought it was very, very impressive. Okay, now I have 13 minutes. Okay. Yeah. So now that we have this theorem ready, so this a k xi, at least we got the formula for a k xi 0, like using the Fourier transform. So what more can we say about this a k xi 0, the parallel section function? Again, to remind you, we had this, and the areas of these cross sections was effectively defining this a k xi t. So one thing, Brunn's theorem tells you a very intuitive fact, that at the central hyperplane section for a convex body is the maximum. And the proof, of course, wants us to dot the i's and cross the t's and so on. But you can believe that this is true, that the central hyperplane cross section is actually the maximum amongst all these things. And if this is a smooth convex body, a k xi will actually be a smooth function. And smooth, by that I mean the boundary is smooth and so on. Then this fact, like from very basic calculus, kind of tells you that the second derivative has to be less than or equal to 0. That a k xi double prime 0 is less than or equal to 0. So this is what Brunn's theorem states, and it's a very like believable fact. Okay, and another point I want to make is convexity. Like, can we say more? Like, for example, what about third derivatives and so on? Like, can we say more about that? But typically, convexity doesn't control much beyond the second derivative, and in fact, that is going to play a big role in the final answer. Like the fact that when you, let's say you talk about Jensen's inequality and like convex functions and so on, you talk about second derivative being bigger than or equal to 0 and so on. But third derivative and beyond, there is not much control given by the fact that a function is convex. Okay. So yeah, I'm not going to, again, those will be technical details. So I'll not be going into the proof of this theorem, but this theorem is effectively telling you that you can, in fact, just like we did for a k xi 0, like we actually computed a formula for that, and there k was equal to 0, right? Like k was 0 in a previous case, so you can actually do better. You can actually compute a formula for the derivatives of a d xi at 0 for the kth derivatives in terms of Fourier transforms, but of course the functions will change. Instead of having norm k, norm xk to the minus n plus 1, you'll have a minus n plus k plus 1. And you have these terms, minus 1 to the k over 2, pi times n minus k minus 1. This is for even integers. And for odd integers, you have, and you can imagine these are like Taylor series expansions kind of. And the proof actually involves kind of going into the complex plane. Like you define, in fact, these formula hold true. I just specified for integers because that will lead to our solution. But this is actually true for fractional derivatives. Like k you can take to be some like complex numbers. You can give a definition of fractional derivatives in that sense, and you can do some analytic continuation and extend. And as you can guess, this k not equal to n minus 1 kind of gives you some sort of essential singularity, which was not be able to remove by this kind of procedure. And if you want to straight away see from this, if you put k equals n minus 1, this becomes just the constant function 1, right? And the Fourier transform of a constant function will give you some version of the delta function. So like not really a function. So in that sense, it would be too much to expect that you'll have a formula for that here. Like the n minus 1 derivative has to be a function on the right hand side, but somehow here you don't have a function. So yeah. Anyway, so and these proofs, if I may say, they are not like extremely involved. They're very cute and very like sweet. Like they're just the right amount of computation involved. So once you have this result, so remember that here we're talking about second derivatives and controlling convexity and so on. So here, this gives you a formula for figuring out how fast things are changing using Fourier transforms of certain functions. Okay. All right. So another notion we have to introduce here, which will effectively tell you it is like a, what's that called? It's like a messenger between the final resolution and the things we're talking about now. So let K and L be origin-symmetric convex bodies. So we have this notion of duality, you could say, like some sort of a dual body of L. So remember that we're talking about hyperplane, central hyperplanes, but there is nothing stopping us of talking about central subspaces of dimension K for any K. In fact, if K is equal to 1, it is effectively giving you this radial function, right? It is telling you that I'm looking at one-dimensional subspaces and the width. Effectively, I'm looking at this width. So you can talk about all these cross-sections at all dimensions. So you can ask the question, okay, is there a body L whose function, and by the way, the space of the central hyperplanes is actually isomorphic to the space, like the space of n-1 dimensional things is naturally isomorphic to the space of one-dimensional things just by the inner product. Like you take the orthogonal things, and same with K and n-k dimensional things. So that is the kind of duality that is being tried to express, that we're trying to express here. That if I have this K, object K, origin symmetric convex body K, whose central hyperplane sections have this kind of formula, is there a body L whose actual radial functions look like the same thing? So this is the way I'm expressing it. Like this is the radial function. So this is the, so that's the relation between K and L. And again, this parenthetical equality is something which we have already seen, that these cross sections have a formula in terms of this particular function. And this is where this positive definite distributions comes in, that an origin symmetric convex body has this sort of dual body. It is not true that it will always have such a dual body. It has such a dual body if and only if this Minkowski functional to the -1 represents a positive definite distribution on Rn. And remember, this is no minus n+1 or anything. It's just a fixed number, -1. So one way is easy to see, right? Because if you know that this is actually a function, you take the inverse Fourier transform of this, or rather, these are even functions. So Fourier transform and inverse Fourier transform are very similar. So let's take of the left-hand side. And I want to say that this is actually a positive definite distribution, meaning this will be a positive function, so to say. But if I do this, what do I get on the right-hand side? Some constant times just this L to the -n+1, right? Which is trivially a positive distribution. Like if you acted on like positive Schwarz function, this is just a nice function, right? So this tells me that this norm xi k inverse is actually a positive definite distribution. So one way is obvious, that if you have a dual body, then you have norm this k inverse represents a positive definite distribution, simply because we actually explicitly know what its Fourier transform is. But conversely, you can pretend that you can take all these Fourier transforms and define something like this, and this will define a convex body. But there is a catch here, and that is the fact that it will no longer be a function like this, because typically, if you remember, this was version of the Bochner theorem was this norm k inverse is like a measure. So you have to modify your proof a little bit, but not too much. So, but intuitively you can believe that if this were actually a function, like a positive function, then this is, you could straight away explicitly give this formula, and then this will in fact and xi, by the way, is on the sphere, so this will actually define a convex body. Okay. So now we have two corollaries. Every origin symmetric convex body in R4 has a dual body. So let's focus on that. We'll come back to corollary 15 later. So why is that? So remember the formula we had here. Double prime 0 is less than or equal to 0. But I also had this formula that AK double prime, if I equals to okay. Okay, yeah.
Recording is on.
Okay. Yeah, so again, like coming to corollary 14. So essentially, here what we have shown is that every origin symmetric body has a dual body if and only if this particular thing represents a positive definite distribution. And so the claim here is origin symmetric convex body in R4 always has a dual body. And again, so the connection here is effectively built by this theorem we have, that if we plug in k equals 2 here in this result, what do we get? From the Brunn's theorem, we know that this second derivative, so k equals 2 will mean this is second derivative, by the k is even, so this is the case we are in. And this minus n plus k plus 1 becomes minus n plus 3 when we put in k equals 2. So when I plug in n equals 4, so minus 4 plus 3 becomes minus 1. And minus 1 is the exponent we really want when we talk about dual bodies. And we want this to be a positive definite distribution for it to have a dual. So again, this reduces to the fact that the right-hand side must be a positive function. If the left-hand side has to be, like if the norm k to the minus 1 has to be a positive definite distribution, the right-hand side better be a positive function. And that we have because this is negative, minus 1. And from here, the second derivative, because it was a maxima, so second derivative was negative, so product of two negative things, you have positive. So hence we have that for dimension 4, norm x k to the minus 1 is always positive definite for no matter what origin symmetric convex body you have. So please say yes if this is fine, because I don't want to keep on. Is this okay?
Yeah.
Okay. All right. So now we talk about corollary 15. So which says that in dimension 5 there is actually a counterexample, meaning there is a origin symmetric convex body which does not have a dual body. And as of yet, we have not connected it to the Buseman-Petty problem. We will do it in the next slide. For now, it's all about origin symmetric convex bodies and whether their dual bodies exist or not. Okay. So again, coming back to this formula, let's put in k equals 3, n equals 5. Note that this is a dimension, n equals 5. So if I do that, what do I get here? Again, minus 1, right? Minus 5 plus 3 plus 1, minus 1. And that's what I want. But on this side, I have a formula. And I want to claim, if I want to say that it has a dual body, I want to claim that this function is always positive. This whatever a, d, xi, g, z and all this thing, this is always positive. That's what I want to claim. But that is not true. You can actually find a d and a xi where this is not true. It will actually be negative for some of these directions, this function. So again, using this result right here, it proves that you can have a counterexample. And I will not exactly explicitly give you that counterexample, but it is not super exotic. Of course, it's effectively of the form you find a function in one dimension f, and you define this cylindrical type of object. x1 squared plus whatever x4 squared is less than or equal to f of x5. And that will effectively violate this positivity here. And by equivalence in this slide, dimension 5, which does not have a dual body. And again, that will hold for higher dimensions because all you have to do is build some small, big, like cylinders or something like that. So you can use this counterexample to build more and more counterexamples in higher dimensions. So yeah, so this brings us to the answer, which is given in theorem 16, which is that if K is an origin symmetric convex body which has a dual body, then the Buseman-Petty problem is affirmative. Meaning, like if you give me any other origin symmetric convex body L, and it satisfies this condition that n-1 dimensional cross sections dominated, L dominates K, then the total volume will dominate K. And from what we saw previously, since up to dimension 4, everything has a dual body. That means Buseman-Petty problem is affirmative for n less than or equal to 4. And theorem 17 again says that if something does not have a dual body, then first of all, you can approximate it with an infinitely smooth origin symmetric convex body with strictly positive curvature. That is, again, does not have a dual body. So you have something without a dual body, then you move it a little bit, you get another thing without a dual body, which is nice. And that nice thing can be perturbed to give a counterexample to the BP problem. So effectively, since this is the theorem which is relating the existence of dual bodies with the resolution of the Buseman-Petty problem. So the answer is that for n less than equal to 4, that you have this kind of Cavalieri kind of thing holding, but beyond n, like n5 and all, the Cavalieri principle does not hold. And I'll just quickly show you the proof of theorem 16, just to illustrate how sweet and simple it is. It's not something super complicated. And right now I just need a nod to say that I'm on the right track, because this is the last slide.
Yeah. Go ahead.
Okay. All right. So we will prove this result that if everything has a dual body, then this Buseman-Petty thing is true. Sorry, I heard a noise. It's a phone probably. Okay. So remember that the spherical Radon transform actually gave you these cross sections, right? We had this formula like from the very beginning. This was our main formula. Like the central hyperplane cross sections can be represented using these spherical Radon transforms. And if I'm saying that one of the cross sectional areas dominates the other, is essentially saying that spherical Radon transform dominates the other. Now here I'm using the positive definiteness of inverse. Like since K has a dual body, remember that we said that norm K inverse has some sort of is a positive definite distribution. So there is a finite positive measure from the Schwarz theorem, like the equivalent of Bochner's theorem, that R mu is this. So so here if you look at the formula for the volume, the formula for volume is like if you look in polar coordinates, it's like integrating this function, norm xk to the minus n over the sphere, and then of course you have to integrate 0 to infinity. And whenever you see this inner product kind of thing, just think you're multiplying functions and integrating them over Sn minus 1. So now, so now you have this R mu dotted with this function. This is exactly formula volume, because this R mu is effectively this thing, and the product will give you norm xk to the minus n. So this is just a straightforward formula, polar formula for the volume. Now using the self-duality of R, you can move the R to the other side. So you have mu dot this. And remember, mu is a finite positive measure. So now that will become important. So since mu is a finite positive measure, then, and since you have this domination thing going on here, you can have this inequality. Mu dot R of this norm K to the minus n plus 1 is less than equal to mu dot R norm L to the minus n plus 1. Okay. And here again, I use self-duality, bring the R back to the mu. So R mu again, just remember that it is norm xk to the inverse, but I want to compare volumes of K and L. So I want exponents of n in both. So I choose my Holder exponents the right way and use Holder's inequality. So R mu looks like a complicated thing, spherical Radon transform of a measure, but it's just this thing. So now that you have, I think I missed out an integral 0 to infinity here. So this is just the polar form. And eventually you end up with n times volume of K to the 1 over n times volume of L to the n minus 1 over n. You move things around and you conclude that volume of n of K is less than equal to volume of n of L, which is exactly the statement of theorem 16. Okay, somehow it's theorem 15 here, but it's a statement of theorem 16 saying that if K is actually an origin-symmetric convex, it has a dual body, then you have the Buseman-Petty is just fine. It just holds true. And again, this finishes the problem. And this is where I would like to end my talk. Thank you all for your patience amongst all these internet issues. And the last remark is that this talk actually cured me of my cold.
Okay, so are there some questions for Soumyashant before we end?
One question.
Yeah, go ahead, Rajiv.
So somehow the existence of dual bodies seem to be playing a key role, right?
Yes, that's true. Yes. Can you hear me?
Somehow the existence of a dual body
Yes,
seems to be playing a key role in this.
that's right.
So can you just elaborate on that?
Uh, you mean
Yeah, geometrically, what does it
you know,
mean? I mean, for example,
mhm. I mean, I guess like in a broader picture, of course, like technically we saw what it meant, like in the sense the existence of dual bodies typically
yeah,
meant
yeah,
that like
yeah. But
Fourier
is there a
transform had a
geometric or some intuition behind that?
Yeah, unfortunately, yeah, I don't know of that. But I do, one thing I can tell you that these kind of dual body results also are like hold in the sense of like other dimensions, not just one dimension, like k dimensions, n minus k, and up to certain dimensions, depending on k, you have a dual body, and beyond that, it's not. But I don't have a good like English way of saying what it means. Yeah,
Okay,
sorry.
okay, okay.
Yeah,
Yeah.
Yogesh had a question.
Yogesh, you want to ask something? No.
Okay, I think maybe.
Okay. Are there any other questions? Okay, if not, let's just thank Soumyashant for this talk.
Thank you.
Okay, so I'll end the recording now.